Hello everyone and welcome to Math 37 online lecture. The topic for today is absolute convergence, conditional convergence, and the ratio test. As always, I'm going to start with a quick recall of where we're at. So we've been covering so far a series, which is an infinite sum of a sequence, which we denote as follows. So starting at k equals 1 to infinity of ak. And then we also defined what it means for a series to converge to L or add up to L. So we said a series converges to a value L if the limit of the partial sums, the sequence of partial sums, as n goes to infinity, is equal to L. And if this limit, the limit of the partial sums does not exist, then we say that the series diverges. In the last lecture, we talked about alternating series. Alternating series, which have the following form. So it's minus 1 to the power of k, ak, where k equals 1 to infinity, or minus 1 to the k plus 1, ak, k equals 1 to infinity. And here, ak is a positive sequence. So intuitively, an alternating series is just a series, a sum of infinite numbers where the terms are positive, negative, plus, minus, and so on. And then we talked about the alternating series test, which was a test, alternating series test. So given an alternating series, we could use the alternating series test to determine if this alternating series converges based on some conditions that the sequence AK needs to satisfy. Today we're going to start by talking about absolute convergence and conditional convergence. So let me get started with the definition. We say a series AK equals 1 to infinity is absolutely convergent. If the series of absolute value ak k equals 1 to infinity converges. Alright, so the series AK is absolutely convergent if the series absolute AK converges. One thing to note is the property of being absolutely convergent is a property of the series, the original series AK, and it depends on whether the series absolute AK converges or not. And closely related to that, the definition of conditionally convergent. So we say a series AK is conditionally convergent if conditionally convergent if the following are true. So one, we require that the series is convergent, right? Conditionally convergent, so it has to be convergent. AK is convergent. And two, the series of absolute value AK is divergent. So if both these conditions are true, that is, the original series is convergent, but the absolute value of the series is divergent, then we say that it's conditionally convergent. So let me start by talking or giving a few basic examples on absolute and conditionally convergent. So the first example, show that the series k equals 1 to infinity of minus 1/2 to the k is absolutely convergent. Convergent. So if you recall from a previous lecture, this actually is a geometric series, and using the theorem we did on geometric series, you can show that this series converges. But absolute convergent and convergent are not the same thing, right? By definition of absolute convergent, what we need to check, that the series of the absolute values, so absolute value minus 1/2 to the k, we need to check that this series converges. Right. And this series, if I just simplify a little bit, is just equal to k equals 1 to infinity of minus 1/2 to the k, which is equal to simply 1/2 to the k. So now, does this series converge? And if you look closely, this is again a geometric series. So this is a geometric series. With r equal to 1/2, right? And if you recall from the theorem on geometric series, if the absolute value of r is less than 1, then the geometric series is convergent. And in this case, since absolute value of r is equal to 1/2, which is less than 1, this series converges. Right. So this is enough to show that the original series, therefore the series minus 1/2 to the k equals 1 to infinity, is absolutely convergent. The only thing we needed to check is that the series where we take the absolute value of each term is convergent series. Now let's do an example for conditionally convergent. So example, show that the alternating harmonic series, if you recall, the alternating harmonic series is minus 1 to the k over k. So show that this series is conditionally convergent. So for this, we need to check two things. First, we need to show that the series converges. So show that series converges. And the way we do that is we note that this is an alternating series. It's an alternating series with ak, with our positive sequence being ak is equal to 1 over k. Right? And I actually did this example last time, so I won't get into too much detail again, greater than 0. But ak in this case is strictly decreasing, and it has a limit going to 0. Right. And I show this in more detail in my series on in my video about alternating series. But these two conditions imply that the series is convergent by the alternating series test. So by AST, it implies that the series 1 over k is convergent. Right. So that's the first thing we need to show. The second thing we need to show is that the series of absolute value diverges. So we need to show that the series absolute value of minus 1 to the k over k equals 1 to infinity. And let me just simplify that right now. So this is equal to, I could distribute the absolute value between the numerator and the denominator. So this is minus 1 to the power of k over k. which is just equal to the harmonic series 1 over k. Right, so we need to show that this series diverges. So we've encountered the harmonic series a few times before, and we know that again, I won't show it because I've shown it multiple times in the past, but we know that the harmonic series diverges. And you can say it's by the p-series theorem. So again, refer to one of the previous videos for the proof of this. But now that we've shown that the original series converges and the series of the absolute value diverges, that implies that this series, so the original series, minus 1 to the k over k, so that shows that this original series is conditionally convergent. Now, one thing you may be wondering is, why is it that in the conditionally convergent case we had to check that the original series converges and then the absolute value series diverges, but in the absolutely convergent case we only had to check that the absolute value series converges. And the reason for that is actually because absolute convergence, if we just check that the absolute value of the series converges, that gives us the original series converges. So theorem. If a series is absolutely convergent, then it's convergent. And if we unravel a definition of absolutely convergent, another way to write this would be, so i.e., if the series absolute value of ak, k equals 1 to infinity, converges, then this implies that ak converges. Right, so by this theorem, we don't need to check that the original series converges. As long as we check that the absolute value series converges, then we know that the original series without the absolute value converges. Right, and the proof for this will actually be in the next assignment. So I won't do it here, obviously. But another noteworthy thing about this theorem is the contrapositive. So the contrapositive to this statement, this theorem, is positive, is that if the series ak, k equals 1 to infinity, diverges, then that implies that the absolute value series also diverges. Right, so a series being divergent automatically implies that the absolute value series is also divergent. And from this, let's make a table of the different properties for convergence, absolute convergence, conditional convergence, and divergent. Right. So we say the series ak from k equals 1 to infinity is the following. So it's absolutely convergence if the original series converges. So converges. The absolute value series also converges, and this is by the previous theorem. The previous theorem tells us that we need to check this, so need to check, but we don't need to check this. I mean, if you check this, it won't tell you that the series is absolutely convergent. It'll just tell you that series is convergent, so don't need to check. Again, we don't need to check it to show absolute convergence. In the conditional convergence case, we say that the series AK is conditionally convergent if the original series converges, but the absolute value series diverges. And in this case, we need to check both. So we need to check this, and we need to check this. And finally, to say that a series is divergent, the series diverges, and we need to check this. And the absolute value series also diverges, but we don't need to check this. Or, I mean, again, we can check it, but it won't tell us anything about divergence. Don't need to check. Right, so actually I'm going to change the word check to show. So in the absolutely convergent case, you don't need to show that the original series converges, even though it does, but you do need to show that the absolute value series converges. In the conditional convergence case, you need to show that both the original series converges and that the absolute value series diverges. And in the divergent case, you only need to show that the original series diverges, which will imply by the theorem on the last page that the absolute value series diverges. So effectively, we've split up the property of convergence into absolute convergence and conditional convergence, and we've left the property of divergence as a standard. So let's see an example. Let's consider the series starting at k equals 2 to infinity of minus 1 to the k over k ln k. And the question is this conditionally convergent, absolutely convergent, conditionally convergent, or divergent? Right. So in this question, since we don't know whether the series will be absolutely convergent, conditionally convergent, or divergent, we need to consider both the series. We need to consider both the original series, which is just minus 1 to the k ln k, and the absolute value series. To the k over k ln k from k equals 2 to infinity. Right. So let's start with the original series. So consider original series k ln k. Okay. So note this is an alternating series. This is alternating series because we have the minus 1 to the power of k term. Alternating series. And the corresponding positive sequence is ak is equal to 1 over k ln k, right? And this is a positive sequence. So we can try using the alternating series test, and for the alternating series test, we need to check two things. We need to check that the sequence ak is strictly decreasing, and we need to check that the limit of that sequence is 0. So let me go to the next page, and let me actually write the series in a corner here. So ak is equal to 1 over k ln k, and we want to show that this is strictly decreasing, and the way we do that is first observe that k plus 1 is greater than k, which implies that 1 over k plus 1 is less than 1 over k. And similarly, a ln of k plus 1 is greater than k, ln k, which implies that 1 over ln k plus 1 is less than 1 over ln k. And both these statements are true for all k greater than or equal to 2. This statement is true for all k, but all positive k, but k greater than. Right. So if I multiply these two inequalities, so multiply inequalities, I get that 1 over k plus 1 times 1 over ln k plus 1 is less than 1 over k, 1 over ln k. And this is equal to ak, and this term is equal to ak plus 1. And this is true for all k greater than or equal to 2. Therefore, ak, the sequence, is strictly decreasing. Okay, and next we need to consider what the limit of the ak is. All right, so we need to compute the limit as k goes to infinity of ak, which is equal to the limit as k goes to infinity of 1 over k ln k. Right. And this we can do using the squeeze theorem. So we have that ln k is greater than 1 for k. This is true for k greater than e, but since it's an integer, let's say k greater than or equal to 3, which implies that 1 over ln k is less than 1, so 1 over k ln k, which is the limit we want to compute, is less than 1 over k. And this is this is greater than 0. So this implies that by squeeze theorem, since both the bounds have limit, so limit as k goes to infinity of 0 is equal to limit as k goes to infinity of 1 over k, which is equal to 0. This implies that the limit as k goes to infinity of 1 over k ln k is equal to 0. Right? So since this limit is equal to 0 and it's a decreasing sequence, ak, by the alternating series test, the series converges. K over k ln k converges. Right, so this is k equals 2 to infinity. Okay. Now, if we had gotten that this series diverges, we would be done, right? Because then we would say that the series is divergent. We don't need to show that the absolute value series is divergent. But we got that this series is convergent. And now we need to check whether this is absolutely convergent or conditionally convergent. And to do that, we need to consider the absolute value series. So now we consider the absolute value series, which starts at k equals 2 to infinity of the absolute value of minus 1 to the k ln k. And what the absolute value series does here is it gets rid of the minus 1 to the k. So you're just left with 1 over k ln k from k equals 2 to infinity. And furthermore, you can see that this is equal to the series f of k equals 2 to infinity, where f is for f of x equal to 1 over x ln x. Right? So now we're going to try to apply the integral test here. And to apply the integral test, well, first we need to know that f is continuous, and in this case it is. So f of x is continuous because x and ln x are not equal to 0 for all x greater than or equal to 2. Again, our starting index is 2, so we only need to look at x greater than or equal to 2. Also, f of x is decreasing for all x are in 2 to infinity. And the way we see that it's decreasing is actually, I've already shown it here, right? So this, this process here will also work to show that the function is decreasing, even though here it's just used for integers. right? So that's how you show it's decreasing. And finally, so this is already shown above, or previously on the previous slide. And finally, I need to check that this series is positive, or this function is positive. And that's also apparent just by looking at the function, because x and ln x are positive, greater than or equal to 0, which implies that they're, if you put them in the denominator, they'll be positive. Is greater than or equal to 0 for all x in 2 to infinity. Right? So therefore we can use the integral test. Right, so let's do that. So we need to consider the integral, consider the integral 1 over x ln x dx from x equals 2 to infinity. Right? This is equal to the limit, by definition, as a goes to infinity of the integral from 2 to a of 1 over x ln x. Right? And if you remember from the integration unit, we can find the antiderivative of this using the substitution u equals ln x. And the answer we get from that is, so let me write the limit as a goes to infinity. The antiderivative of this function is actually ln of x. Right? And we want to take the integral from 2 to a. Right? So this is equal to the limit as a goes to infinity of ln of a minus ln of 2. Right? And this is equal to, well, the first term goes to infinity, because as a goes to infinity, ln of a goes to infinity. So this is actually equal to infinity, i.e. this diverges. Integral diverges. So therefore, by integral test, the series also diverges. So the series is 1 over k ln k. Which in this case is equal to the absolute value series. Right, these diverge. So since the original series converges and this one, the absolute value series, diverges, that implies that the series in question is conditionally convergent. Is conditionally convergent. Okay, so now that we've talked about absolute convergence and conditional convergence, we can now introduce the ratio test. So let me first write down the ratio test. And this is the ratio test for absolute convergence. And what this test says is, suppose you have a series, ak, k equals 1 to infinity, such that none of the terms are 0. So ak does not equal 0 for all k. So it has to be a series with non-zero terms. And suppose that the limit as k goes to infinity of the ratio of the absolute value, so ak plus 1 over ak, exists, and suppose this limit equals L, right? So what the ratio test tells us is, one, if the value L is less than 1, strictly less than 1, then the series converges absolutely. So then AK converges absolutely, or is absolutely convergent. Okay. 2. If L is strictly greater than 1, then the series diverges. Okay. And lastly, 3, if L equals to 1, then this test is inconclusive. So we can't say either. We can't say whether the series converges, diverges, converges absolutely. We cannot. The test is unconclusive. So the nice thing about the ratio test is that it works for any series with non-zero terms. They can be positive, they can be negative, they just can't be zero. So before I do an example, let me give a brief sketch of the proof. I'm not going to prove it with the full details, but let's say, let's prove the first statement. Right. So suppose L is less than 1. So if L is less than 1, what we want to show is that the series is absolutely convergent. So we want to show that it's absolutely convergent, which by definition means we want to show that the series absolute value AK equals 1 to infinity is convergent. So this is what we want to show. Right. So how do we do that? So what I'm going to do is I'm going to pick an R such that R is between L and 1. Well, I know that L is less than 1, strictly less than 1, which means that there must be some number R between L and 1. Right. Now, since R is between L and 1, and we know that the limit, so we know that the limit as k goes to infinity of the sequence AK plus 1 over AK absolute value is equal to L, this implies that eventually it's going to be sufficiently close to L, which means that eventually it'll be less than R, the terms of the sequence, that is. So eventually AK plus 1 over AK absolute value will be less than R for all k greater than some n. So to show this, again, this is a sketch of a proof. I'm not doing the full formalities, but if I draw out the sequence, so this here is k, and this here is the value of the sequence, and I have L over here, this is 1, and then this is R, and the sequence, say, looks something like this. So I don't know, I can just jump around. But we know that eventually, even if it's even if the sequence is going above R, let me make these darker. Eventually, since it's approaching that line L, it will eventually just it'll be less than R. So a good exercise would be to show this exercise. Show this formally using the epsilon definition of limit. Show this rigorously. Okay, but now that we have that AK plus 1 over AK absolute value is eventually less than R, we can say that, so we have AK plus 1 over AK is less than R eventually, so for all k greater than n. Well, this implies that AK plus 1 is less than R times AK for all k greater than n. But also, if I apply this argument to ak plus 2, because we also know that ak plus 2 over ak plus 1 is less than r, we have, so let me write this down actually, also ak plus 2 over ak plus 1 is less than r for all k greater than n. Well, this implies that ak plus 1, plus 2, sorry, is less than r times ak plus 1. Right. But from the above line, we know that ak plus 1 is less than rak, so this is less than r squared ak. And repeating this process over and over, so by induction on k, we have that ak plus, ak plus, let's say I is less than r to the power of I times ak. And this is true for all k greater than n. So we can take k equals n, k equals, let's say n plus 1, k equals n plus 1, and in that case we get that a of, well, n plus 1 plus I should have chosen n here, but that's okay, is less than r to the I a n plus 1. Okay. Okay, next, so we're going to consider the geometric series r to the k, where k goes from 1 to infinity. Or actually, rather, k equals 0 to infinity. K equals 0 to infinity. So this is a geometric series. And if you recall from the lecture on geometric series and the theorem on geometric series, in this case, since the absolute value of r, which in this case is just equal to r because r is positive, is less than 1, because, again, we picked r to be between L and 1. So since this is less than 1, this series converges. And again, that's by the geometric series theorem. So this then implies that the series an plus 1 times the geometric series rk, which by the product constant multiple rule is equal to the series an plus 1 times r to the k, from k equals 0 to infinity. We know that this series converges by the constant multiple rule. Now from the last slide, we also showed that an plus 1 plus I for all I is less than r to the I, times an plus 1. And this is true for all I greater than or equal to 0. And of course we know that both these terms are greater than 0 because we're taking absolute value. So that means that we can apply the comparison test here. So by a comparison test, the series k equals 0 to infinity of an plus 1, so I'm doing a change of index here from I to k, converges because the greater series converges, because r to the k an plus 1 converges. And what is this this series here? So if we expand this out on the next page, so we have the series an plus 1 plus k starting at k equals 0. Oops, absolute values. K equals 0 to infinity. Well, this is equal to, when k is equal to 0, then it's just an plus 1 plus an plus 2 for the k equal 1 term, plus an plus 3, and so on. So this is actually equal to the series, if I do a change of index, I start at k equals n plus 1 of ak all the way up to infinity. And we just show that this converges. And this, of course, is a tale of the series that the original series that we wanted to show converges. So this implies that so by tale of series theorem, right? This implies that the whole series converges starting at k equals 1. Converges because its tail converges. Because tail converges. Right. So therefore, the series is absolutely convergent. So therefore, ak from k equals 1 to infinity is absolutely convergent. Okay. So that was the proof for 1, namely L is less than 1. The L is greater than 1 and L is equal to 1. Well, L equal to 1 is just saying the test is inclusive, but the L greater than 1 case, I'll leave that as an exercise. It's similar to this, but you just show that the series diverges instead of absolutely converges. Okay, but let me do 2 quick examples. So the first example, let's consider the powers, the series k equals to 1, starting at k equals 1 to infinity of k over e to the k. Actually, let's make it an alternating series. So minus 1 to the k times k over e to the k. Right? So we want to show that the question is this absolutely convergent or divergent? Now, you may just be asked the question, is it convergent or divergent? In that case, you can still use a ratio test because absolute convergence implies regular convergence. But in this case, I'm asking you, is it absolutely convergent or divergent? Well, first we got to see if we can apply the ratio test here. So the ratio test works for a series with non-zero terms, and in this case, the series has non-zero terms, right? Because k over e to the k does not equal 0 for all k greater than or equal to 1. Because if k is greater than or equal to 1, the numerator is obviously non-zero. And of course the denominator is e to the k is always non-zero. Right? So series has non-zero terms. Right? And the second thing we got to see is, does the limit of the ratios exist? Right? So let's consider the limit as k goes to infinity of ak plus 1 over ak. And in this case, this is equal to a limit as k goes to infinity, the absolute value of minus 1 to the k plus 1, k plus 1 over e to the k plus 1 times minus 1 to the k, k over e to the k. Right. And this is actually equal to, if I simplify, just minus 1 times, oops, I forgot the limit, is equal to limit as k goes to infinity of minus 1 times k plus 1 over k times e to the k over e to the k plus 1. And I can take the limit, well, the minus 1 goes away because of the absolute values, and then I can split up the limit among the two terms. So this is equal to limit as k goes to infinity of k plus 1 over k times the limit as k goes to infinity of e to the k over e to the k plus 1. Well, the first limit here is just 1, and the second one is just 1 over e, so this is equal to 1 over e. So the limit of the ratio does exist, right? And since the limit of the ratio, or the absolute value of the ratio of ak as k goes to infinity is equal to 1 over e, which is strictly less than 1, the series is absolutely convergent. Absolutely convergent. Okay, so that's how you use the ratio test to show something's absolutely convergent. Let's do one more. So let's do another example. Let's consider now the series 3 to the k over k factorial, where k goes from 1 to infinity. And the question is this convergent or divergent? Or divergent. Right. Now again, we can use the ratio test here, because if we find that it's divergent, well then it's divergent. But if we find that it's absolutely convergent, we know absolute convergence implies regular convergence, right? Ratio test works here. But first we need to see if the conditions of the ratio test are satisfied. So again, the first thing is, does it have non-zero terms? Well, 3 to the k is not equal to 0, and k factorial is not equal to 0 for all k greater than or equal to 1, which implies that the terms are not equal to 0. So this is for all k greater than or equal to 1. Right? So series has non-zero terms. Okay. And secondly, we got to check the limit of the ratio, or the absolute value of the ratio. So limit as k goes to infinity of ak plus 1 over ak. Well, this is equal to the limit as k goes to infinity of 3 to the k plus 1 over k plus 1 factorial over 3 to the k over k factorial. Again, simplifying this, I'll get that this is equal to the limit as k goes to infinity of 3 over k plus 1 over 3 to the k times k factorial over k plus 1 factorial. Okay, and this is equal to, well, the first term is just equal to 1/3, or rather 3, sorry. And the second term, well, k factorial over k plus 1 factorial. K factorial is the product of all integers up to k, and k plus 1 factorial is the product of all integers up to k plus 1. So if you cancel out everything up to k, you're just left with a k plus 1 in the denominator. Right? And as k goes to infinity, this is going to equal to 0. So again, by the ratio test, so the limit exists, so we can use the ratio test. So by the ratio test, since the limit is a limit of the ratio is equal to 0, which is strictly less than 1, this implies that the series is absolutely convergent. And the question is asking us, is it convergent or divergent? So we've proved something stronger. So series is absolutely convergent implies that series is convergent. Okay, so that's how you use the ratio test to show something's convergent. Of course, if you got that the ratio was greater than 1, then we would say it's divergent, and if it was equal to 1, then it would be unconclusive. Okay, and the last thing I want to finish us off today with is a theorem, or is a test, another test called the ratio test, or the root test, sorry, root test. Now you are not responsible for this, so I'm just stating it, it won't be tested on. So you're not responsible for this. But the ratio, the root test, what the root test says is, suppose we have a series AK, and then suppose that the limit, as k goes to infinity of the kth root of the absolute value of AK. Suppose this limit exists and is equal to L. Right. Then very similarly to the ratio test, the root test says is if L is strictly less than 1, then the series is absolutely convergent. Okay. 2, if L is strictly greater than 1, then the series is divergent. And 3, if L equals 1, then the test is inclusive. So that's the root test. Again, you won't be responsible for this. I'm just stating it for your knowledge. But that's where we'll end it for today. So thank you for watching. And again, if you have any questions, please post them on Piazza. I follow it regularly, and I can answer your questions as they come up.